Welcome to the Unbalanced Fault Analysis video series. In this video series, we will look into the calculations and analysis of the three-phase unbalanced fault, and it is closely related to the three-phase balanced fault analysis in the previous video series. And if you have not looked into that, I recommend you to look it up. And before we look into the analysis of the three-phase unbalanced system, we have to first understand one concept called the symmetrical components. And under this topic, there are several contexts that we need to set up first. First of all, we know that the three-phase balanced system lends itself to a simple per-phase approach, but this is not directly applicable in the three-phase unbalanced system. Okay, the reason is that in the balanced three-phase system, we know the magnitude of each of the phase is the same and that each phase is 120 degrees apart. Therefore, when solving for the three-phase balanced system using the per-phase analysis, by solving only one phase, we can find out what is the value of the other phases, except that they are 120 degrees shifted from each other. But the same cannot be mentioned for the unbalanced system. But the per-phase analysis is the only way we know how to analyze three-phase system. Therefore, the strategy is to use or to force the per-phase strategy in the unbalanced three-phase system analysis as well. But before we do that, something has to be done to our three-phase unbalanced system, and we need to modify it so that we can apply the per-phase analysis properly. And that modification is performed by using the symmetrical component techniques. And this technique basically breaks down an unbalanced three-phase system into a number of balanced systems. And because the system that has been broken down is balanced, then we can apply the per-phase analysis like what we have applied in our three-phase balance system analysis in this broken down system. These symmetrical components basically allow unbalanced phase quantity, it could be current, voltage, or any other electrical quantities, to be replaced by three separate balanced symmetrical components. So the keyword here is balanced symmetrical components, and we have three. The first one is what we call the positive sequence, the negative sequence for the second one, and the last one is the zero sequence. The positive sequence is notated with 1, the negative sequence is notated with 2, and the zero sequence is notated with 0. And notice how the order of the positive sequence and the negative sequence are quite similar. In the positive sequence, the order is A, B, and C. And in the negative sequence, it is A, C, and B. And this is something that I'm sure most of you have learned in circuit analysis. And you also know that the phase angle is measured counterclockwise from the horizontal line over here. And in the zero sequence, there will be no phase angle difference due to their arrangement as such. So now we look into the relationship between them in more details. So by looking into the positive sequence, we established that the IB, the phase B of the positive sequence, is equals to phase A, but 240 degree displaced by this. IC is equals to IA, but 120 degree apart. And if I say that 120 degree phase angle over here is equals to A, then the phase angle 240 is equals to A square. So basically this has to do with the calculations of the complex number, which says that the square of the phase angle is actually equals to the multiplication of the angle value by 2, okay, such as like this. This relationship is also given over here. If A is equal to this and A squared is equal to this, then A cubed is equal to this, and 1 plus A squared is equal to 0. So these are some important properties that you might want to bear in your mind. And this is the relationship for the negative sequence. The way we derive this is similar to what we have derived in the positive sequence. And in the zero sequence, then there is no phase difference between phase A, B, and C as shown over here. Therefore, we can write that IA0 equals to IB0 and equals to IC0. And remember what we mentioned just now, that the three unbalanced phase current is broken down into three symmetrical components of positive, negative, and zero sequence. And another relationship can be formed. That is, the phase of each current, A, B, and C, is actually equals to the summations of their respective phase in each of the symmetrical components, such as like this. IA is equals to IA0 plus IA1 plus IA2. And the same can be said for the other two phases, where IB equals to IB0, IB1, and IB2. IC is equals to IC0 plus IC1 plus IC2. And instead of writing them in 9 different symmetrical components and phases, we can instead rewrite this in terms of phase A only, based on the relationship that we have derived over here. For example, I can rewrite IB1 over here as A squared IA1. I can rewrite IC2 over here as A squared IA2. And remember, the 2 over here does not represent square, but represents the negative sequence. So if I rewrite them by replacing this into here, then they look like this. So this equation can be rewritten into the matrix form or rearranged in the matrix form, and then it will look like this one. And this relationship is a very important relationship because this matrix is fixed, and this is what we call the A matrix. And this relationship also shows that by using only the A matrix and also the phase A of all the symmetrical components 0, 1, and 2 only, then we are able to determine what is the phase current of our unbalanced three-phase system. And this matrix, of course, can be rewritten into a more compact manner like this. And the inverse relationship of this will look like this. Okay, this is obtained by rearranging this equation. And A inverse is equals to this. And notice how A and A inverse are quite similar, where in the A inverse, the matrix has the additional 1/3 term in front, and the square is now at different locations. It's not in these diagonal elements anymore. And if we can actually expand this inverse relationship into the bigger matrix form like this, and from here we observe that the zero sequence of the phase A is actually equals to 1/3 of the summations of phase A, B, and C. And this tells us something. This tells us that in the unbalanced three-phase system, when the neutral is not grounded, zero sequence current cannot flow. Why is that so? Because just imagine for a second you have a three-phase system that is unbalanced, and then the neutral is not grounded. In such a system, the unbalanced current has no other way to flow other than in the system only. And in such a case, it will be impossible for us to draw 1/3 of phase A current plus 1/3 of phase B current and 1/3 of phase C current out and sum them up to give us the zero sequence of phase A. Instead, if that same system is grounded through the neutral, then the unbalanced current can flow to the ground through the neutral. And the current in the neutral then is equals to IA0, which is our zero sequence phase A current. And if we can establish this relationship for the current, we can also establish the same for our voltage, and similarly the inverse relationship. And the same can also be mentioned for our three-phase complex power. So basically, three-phase complex power is equals to VI conjugate. And the T over here is to represent transpose of V matrix over here. And the transpose is to allow the multiplications of the two matrices. Okay, so if you have forgotten the calculations of matrix, so you have to revise on that. And we can go ahead and expand this equation by replacing the ABC phase in the symmetrical components using this relationship and also this relationship, and then we will get this. And we can expand this bracket and by putting in the conjugate and also putting in the transpose, and then they will look like this. And the multiplications of the A transpose and A conjugate will give us 3. So this another important or useful property that you might want to know, but you can actually determine them by multiplying these two matrices together. And this tells us something very important, which is this one. And this shows that the total unbalanced power, okay, is basically the sum of the symmetrical components power, okay, of the zero sequence, the positive sequence, and the negative sequence. We can sum them up, and then we will get the three-phase unbalanced power. And this is the illustrations of the unbalanced current when it is broken down into their three symmetrical balanced system. So this is the unbalanced three-phase current with different magnitude between each of the phase, and the angle between them is not uniform. So we can break such a system down into three symmetrical components, and these symmetrical components are balanced. And notice how the phase A, B, and C here, they are all 120 degrees apart over here. So as in the negative sequence, and of course in the zero sequence, there is no phase angle difference between them. So with this, we have established the concept of symmetrical components. So I advise you to actually go through this video multiple times so that you are familiar with the concept of symmetrical components. And in the next video series, we will look into how we are going to apply the symmetrical components into the analysis of our unbalanced three-phase system. Thank you for listening, and I hope to see you in the next part.